Hi. So today I'm going to talk about symbolic determinant identity testing, which I've abbreviated to SDIT. And I'm going to take a very algebraic perspective of this, and we're going to prove a negative result. So I will explain all the terms in the title. So in particular, things that are not familiar to you are probably null cone, and to some extent, what I mean by the symmetries of algebraic varieties. So I've broken up my talk into 5 small pieces. So I will start with explaining to you identity testing problems, in particular symbolic determinant identity testing, SDIT, and their motivation and place and complexity, and why we're interested in them. And then I will, in the second part, I will view these in a more algebraic bent of view and give you a sort of a rephrasing of these problems from a very algebraic perspective that allows us to use uh, ideas from representation theory or invariant theory or algebraic geometry to potentially try and do something about these problems. And then in the third part, I will state our main result with, so this is joint work with Avi Wigderson. So I will state our main result. And then I will give you a little bit of the idea of the proof. Unfortunately, there's quite a few non-trivial techniques involved, and I cannot go into detail about all of them due to time constraints. And then finally, I'll present just a few snippets of some high-level future directions of this of research in this exciting area. So let me start with identity testing problems. So as part of the title, I want to start with the symbolic determinant identity testing. So the problem is as follows, and it's an algorithmic problem. So suppose somebody hands you m matrices of size n by n, and the entries of these matrices are complex numbers, and they want to ask you to take the formal linear combination t1 x1 plus t2 x2 all the way up to tm xm, and take the determinant of this formal linear combination, and they want to know if this determinant is 0 or not, and they want to know if this is 0 as a polynomial in these new variables t1 to tm. Now this condition you could rephrase as asking for this formal linear combination sum of tixi to be singular when thought of as a matrix with entries in the function field in m variables, which we're going to take t1 to tm. Just as something that will come a little bit later, I want to think of the function field as the free commutative field in m variables. So you start with this base field, the complex numbers, and then you try to build the freest possible field, adding no further relations than you really have to with m extra indeterminates, and you will end up with the definition of what a function field should be. Okay, so that's a algebraic perspective that will be useful for us, and I will hold on to it for the time being. So this problem, the symbolic determinant identity testing, I want to rephrase again in a slightly more algebraic perspective. So I want to define a subset of m tuples of n by n matrices, and it will precisely be the subset for which the answer to this above question would be yes. In the sense that this formal linear combination is singular. So you look at all m tuples of n by n matrices such that the formal sum tixi is singular over the function field. And the collection of all such m tuples of matrices is a subset of the vector space of m tuples of matrices, which I'm going to call singular tuples of size n, singular tuples n comma m, n representing the size and m representing the number. And the observation is kind of very simple, that the symbolic determinant identity testing you can think of as membership in this particular subvariety. So the one thing that I hid behind the door is that this particular subset that I defined to you, this subset of m tuples of n by n matrices, is actually a subvariety in the sense that it's cut out by, you can describe it as the zero locus of a collection of polynomials. Okay, but why are we so interested in this problem SDIT? And it goes back to a result of Cabanets and Impagliazzo in the early 2000s, where they showed that if you have a polynomial time algorithm for SDIT, it implies non-trivial circuit lower bounds. It would probably be the biggest step anyone's taken towards P versus NP. And so it's really kind of a fundamental problem in complexity. And maybe to quickly mention, there's an easy randomized algorithm for SDIT, which is to just replace the TIs with random numbers and then take the determinant. That's a randomized algorithm, but trying to de-randomize this algorithm is a really hard challenge. Even in special cases, it's quite difficult. Now, another reason to study SDIT is that it plays an influential role in the subject of geometric complexity theory that's recently become quite popular. Geometric complexity theory is yet again another approach to VP versus VNP, which is an algebraic analog of P versus NP. And the aim here, and to summarize, would be really be to try and exploit the symmetries um, of the determinant and the permanent. And if you work hard enough into this, if you work yourself into this subject, you will start realizing that the symbolic determinant identity testing is actually a central problem even in this geometric complexity theory program. Um, okay, so that's about SDIT. Now, the next step I want to do is I want to make you familiar with a non-commutative version of this entire story, which is what leads to some of the questions we ask. So the non-commutative version, I will look for m tuples of n by m tuples of n by n matrices, but now I'm going to ask for this formal linear combination to be singular over what's called the free skew field. And the free skew field over m variables is again constructed somewhat like the like the function field, which I wanted to think of as the free commutative field, where you don't impose commutativity at all. So you start with this base field, the complex numbers, and then you throw in m extra indeterminates, and you ask for no relations at all, not even commutativity, and you will end up with a skew field, which we call the free skew field. Skew field is another word for division algebra, which is basically a field where multiplication need not be commutative. And so division algebras or skew fields are just as good for linear algebra. The only notion that you don't have is the determinant, but the notion of rank and linear dependence and so on, all of these make complete sense. And so when I talk about this formal linear combination being singular, I am using the definition of rank as a linear independence of columns, or maximal linear, a maximal set of linearly independent, the cardinality of a maximal set of a linearly independent set of columns. Okay, but I don't want to get too much into the free skew field because that's not going to be part of this talk. But maybe mention that membership in this particular subvariety, which I want to say non-commutative singular tuples, is called the non-commutative Edmonds problem, or it's called the non-commutative, which I'm suppressing, rational identity testing. And the really cool result in recent years is that this problem has a polynomial time algorithm, and there are two bodies of work that give that two significantly different algorithms for this. One is by Garg, Gurwitz, Oliveira, and Wigderson, and another is by Ivanios, Kyaw, and Subramaniam. One approach is very analytic in nature, the other approach is very algebraic in nature, and both approaches have their own advantages and disadvantages. But the key feature, whichever approach you take, starts really from the observation that this non-commutative singular matrices is the null cone for the so-called left-right action. Now, the null cone is an algebraic term, which I will explain to you a little bit maybe after this slide. But then let me first explain to you what this left-right action is so that I can tell you what the motivating questions are. So the left-right action is the action of the group SLN cross SLN on m tuples of n by n matrices. Now, if I have a pair of matrices in SLN cross SLN, and then I have an m tuple of matrices in m tuple of n by n matrices, then the action, the P will act by left multiplication on each of these matrices, and Q will act by right multiplication. You can ignore the transpose on a first reading. It doesn't really play that much of a role. So given that in this non-commutative setting, to solve this membership in non-commutative singular tuples, to give a polynomial time algorithm for it, it was crucial that this particular subvariety was the null cone. You could ask the same thing about singular tuples of commutative singular tuples of matrices, which we called SING-NN in the previous slide. And you might ask, is this a null con for some group action? And there are many reasons to expect why this could possibly be the null con for some group action. And basically, whether it was commutative singular, whether you're in the commutative or the non-commutative setting, the reason you might expect this is because these varieties have a lot of symmetries, and which points to the potential of a certain group action, which you can always take advantage of. Uh, okay, so that's the motivating question for us in this talk. But let me be a little bit more precise about why you would want something like this. So the first reason is that we expect null-con membership to have polynomial time algorithms in pretty large generality. I won't state to you in what generality we expect this. You can look up some of the papers on GCT. But the very fact that GCT predicts this means it's interesting to try and figure out which subvarieties are null cons and which ones are not, so that we know which membership in which subvarieties is easy and membership in which subvarieties might be hard. And another reason is that for this null con membership problem, in recent years, following the success of GGOW, we've had exciting uh, new algorithms, and these are based on gradient descent, and they run pretty fast in practice in many cases. And it would be interesting to see if these algorithms, as is, or perhaps with more improvements, could really just be polynomial time. And this was kind of the motivation for trying to understand this particular question of whether this singular tuples of matrices is a null con. So now I've said a few algebraic terms, and so I want to recast everything in terms of algebraic problems without so much reference to where they're coming from and so on. So the complexity is a little bit hidden here, but we'll just hold on to it. So suppose you have a group acting on a variety, on a vector space even, and you pick some point in the vector space, then its orbit is defined as a set of all elements you can take. So you start with this vector small v, you apply all the elements of the group, and you see where all you land up when you take this collection. So that's called the orbit of a vector under some group action. And the null cone is defined as a set of all vectors, so that you look at its orbit and you take its closure, and then you ask whether it contains zero or not. So in other words, it's really saying, look, some vector is going to be in the null cone if and only if you can apply these group elements and in the limit get to zero. So that's what the null cone for. So a null cone requires you to have a group acting on a vector space. And so to any group acting on a vector space, there's an associated subvariety that's called the null cone. Well, the group has to be reductive, but I'm not going to really talk about this notion of reductive throughout this talk. Reductive really just means, I mean, the importance of a group being reductive really comes from just the examples. A lot of groups are reductive, including all the classical groups, whether you take GLN, SLN, SON, SPN, products of them, complex tori, all of these groups are reductive. So in terms of an algebraic problem, the first problem I want to tell you is, suppose somebody gives you a subvariety of a vector space, then you could ask, does there exist a group that's acting on this vector space such that the null cone is precisely a subvariety? And maybe a little snippet here, I might as well take my group to be a subgroup of GLV, because if I want my group to act on my vector space by linear transformations, which I didn't quite say, but that's how I expect my groups to act, then this action will factor through a subgroup of GLV anyway. And so I will think of my groups as just being subgroups of GLV. And now a second question, which kind of looks disjoint from what I've just said, but then I will try to bring it back into context, is suppose somebody just gives you a subvariety of a vector space. Can you determine what are all the linear transformations that preserve this particular subvariety? So I'm looking for all linear transformations on V such that G times, so set of all linear transformations G on V such that GS is equal to S. And this I want to call the group of symmetries of the subvariety S. Now, why are we so interested in this group of symmetries? So the first thing is, it is easy to see might not be immediately clear to you if you've seen these definitions for the first time, but it's not that hard to see that whatever hypothetical group that you might ask, that you might hope for in this first problem A, would have to be a subgroup of the group of symmetries. And so in some sense, problem A is a search for a hypothetical group, and problem B is giving you some sort of a rough upper bound for this first problem A. And maybe from a, if you take a step back and you think about this problem B, uh, no matter what you're studying, understanding the symmetries of the object that you're trying to study uh, has almost always been helpful. Even if it doesn't tell you something new, it maybe simplifies the proofs, or it streamlines our understanding of various things. But knowing the symmetries of any object that you want to study has I think in pretty much almost all cases have been extremely useful. All right, so these are the two algebraic problems I want to focus on. Well, I do want to focus on in the case where this subset S is singular tuples of matrices. And so let me now state the main result. So this is the main result of this paper, and this is joint with Avi Wigderson. So suppose n and m are greater than or equal to 3, and you consider singular tuples. So I consider 3 tuples of 3 by 3 matrices such that their formal linear combination is singular over the function field. Sorry, I consider m tuples of n by n matrices such that the formal linear combination is singular over the function field. Then for any reductive subgroup of GLV, where V is the vector space of m tuples of n by n matrices, we prove that the null cone is not singular tuples of matrices. So this is again one of these questions that you could, it's a negative result, but perhaps what's interesting is the sort of technique. What's really interesting is the sort of techniques we bring to it. At least in terms of the technical content. In terms of the importance of this result is kind of clear, because we really want to find a way to give a polynomial time algorithm for SDIT, which we thought of as membership in singular tuples of matrices. And of course, the importance of that is that it comes very close to P versus NP and so on. And what this particular result is doing, and if I want to just put it slightly a little bit in context, is trying to tell us that there's something structurally different in the commutative setting as opposed to the non-commutative setting that's really bothering us. We don't understand it completely. We know it's not a null cone, but what exactly is the core of the problem is not something we've been able to identify yet. But it does point to like a very structurally, so it's a structural barrier in some sense to giving a polynomial time algorithm for SDIT. Okay, so now maybe I will switch a little bit and try and give you an idea of the proof. So what I really prove in this particular, what we really, the kind of argument we use, because that's also very interesting. So the kind of argument we use is that suppose you take the null cone for some group action, and it happens to be a subgroup of, it happens to be a subset of singular tuples of matrices, then we'll prove that it'll actually be a subset of non-commutative singular tuples of matrices. And then it comes quite easily that non-commutative singular tuples of matrices is a proper subset of singular tuples of matrices under this assumption that n and m are larger than 3. And therefore, your null cone could not be equal to singular tuples of matrices. Okay. So let's quickly take an idea of, so let's quickly go through the steps of the proof. I mean, each one of these steps is quite involved and non-trivial, but I just wanted to give you a really high-level picture of what's going on. So the first step that I do is I compute the group of symmetries for this. So from now on, S is going to be singular tuples of matrices. So I compute the group of symmetries, which just happens to be a GLN cross GLN cross GLM. GLN cross GLN acting by left and right on the matrices, and GLM acts on the tuple as a, there's an M tuple. So the way GLM acts on M tuples of vectors, you can write down the formula that how it acts on M tuples of anything with the linear structure, and that's how it really acts. So what this does is it tells me that the hypothetical group must be a subgroup of this of GLN cross GLN cross GLM. And the second thing that I can really take advantage of is pretty much the only structural sort of result about null cons that we know is called the Hilbert-Mumford criterion. So the Hilbert-Mumford criterion says that if you want to take the null con for this for some reductive group, you start with the null con for an abelian subgroup, a maximal abelian connected subgroup called the maximal torus. So you take the null con for that, and then you move that null con, you move the torus null con by the group, and then that will cover for you the null con for the for the larger group G. Now, maximal connected abelian subgroups are also just known as maximal tori. In the case of GLN, a maximal abelian, whatever, a maximal torus would be just the set of diagonal matrices, diagonal invertible matrices. But perhaps what's really important is that if you look for this null con of an abelian subgroup of a torus, then it looks like the union of coordinate subspaces. And by coordinate subspace, I just mean a subspace where you say certain entries must be 0 and certain entries could be whatever they feel like. That defines a linear subspace, and the null con for a torus will always be a union of such coordinate subspaces. So that gives us some sort of idea as to how a null con really should look. So now I'm going to start being more specific to the case where S is singular tuples of matrices. So the first thing I do is I want to try and give an upper bound on what the null con is. So could possibly be. So I look at all possible coordinate subspaces in singular tuples of matrices. And let me call this L. And then we show that if you took this large group, GLN cross GLN cross GLN, which was the group of symmetries for singular tuples, and I apply it on the union of all possible coordinate subspaces inside singular tuples, then you actually only cover the non-commutative singular tuples. You don't cover all of the singular tuples. And so here's the argument. Suppose you had a null con for some group action that was sitting inside singular tuples of matrices, then this null con happens to be G times the null con for the maximal torus. I don't exactly know what this group G is or what this torus T is, but I know that this group is upper bounded by the group of symmetries. And I know that the null con for the torus is upper bounded by the union of all possible coordinate subspaces. And so so the null con for the group is upper bounded by GS times L, which we know, I said in step 3, I claimed in step 3 is a subset of non-commutative singular tuples of matrices. So once you have that, it means that the null con for the group must actually already be sitting inside non-commutative singular tuples of matrices. So here's the argument that pretty much cleans it up. So you start with, so suppose you had a hypothetical group G for which the null con was equal to singular tuples of matrices, then you know that this null con must already be inside non-commutative singular tuples of matrices. But then non-commutative singular tuples of matrices is a proper subset of singular tuples of matrices. That's what gives you a contradiction. So the explicit example I give you for N and M to be 3 is kind of a basis of skew symmetric matrices. It's kind of well known that it's that this is a singular tuple of matrices in the commutative setting, but not in the non-commutative setting. And if you want if you want to do this explicitly for some case where N and M is larger than 3, then you can find kind of some silly ways to extend this example. So that pretty much completes the proof. And so let me just give a few snippets of future directions. And this I just want to be very high level about, and you should feel free to ask me further. So the first is, given what we've managed to do, kind of a burning question that comes up is, what kind of algorithms do we have for computing symmetries, and how efficient are they? Computing symmetries of varieties in particular. And of course, there's lots of questions you can ask about how a variety is given to you and so on. So the second question is, what next do we do about symbolic determinant identity testing? And there's many things here that you can explore, some of which I've listed down. And the third important direction that I want to point out is, maybe we want to understand more properties of this particular variety, singular tuples of matrices. And this may, from maybe the perspective of commutative algebra or algebraic geometry. And some of these questions might be like, is it Cohen-Macaulay? What is its regularity? What are the ideal generators and so on? All right. So thank you so much for listening to me. That's the end of my talk.